In our last video, we explored several real-world uses of differentiation. Today we'll be examining the antiderivative, also known as the indefinite integral, because it is a reverse process of differentiation. As we discussed in class, integration can be used to find the areas of a region bounded by two curves. But this is just one of many of its uses. Integration is frequently used by forensic investigators to examine car accidents. It is also used to model crash tests through the head injury criterion, to help make driving safer through advancements in airbags. Other applications of integration include calculating the volume of a three-dimensional shape and determining distances. In this video, we'll be examining how fast a car was traveling right before the driver slammed on his brakes to avoid running over a pedestrian. From the information provided at the scene, we will determine the car's velocity at the exact moment the brakes were applied and see if the driver obeyed the speed limit or should be summoned a traffic violation. Through this problem, we will understand the relationship among position, velocity, acceleration, and calculus's close connection to physics. For this lesson, I'll provide a detailed example to highlight how integration is used to determine a car's acceleration and velocity. The question is this: a driver slams on the brakes at a constant acceleration of -23 feet per second squared, resulting in skid marks measuring 300 feet before coming to a complete stop. The driver says that he was traveling at 55 miles per hour right before he hit his brakes. The pedestrian says that this driver was speeding and nearly ran him over. The pedestrian wants the police to issue the driver a ticket, but nothing can be done until the data is fully analyzed. Who's telling the truth, the driver or the pedestrian? If the driver's lying, how fast was he traveling when he slammed on the brakes? Now, because this is such a wordy question, I'll have it projected on the board throughout class so students can always see this. There's a lot of meat here to look at. From earlier lessons, we learned the derivative of position with respect to time is velocity, and the second derivative is acceleration. I will pass this out to every kid in the class. We all have ownership of this. Now, differentiation, displacement goes to velocity, velocity goes to acceleration. When you integrate, acceleration goes to velocity, and velocity goes to displacement. It'll be very useful to have this for all the students so no one gets lost. Now, at this point, we're going to integrate, but before we do that, we're going to do diagram. So as a class, I'm going to ask for volunteers to help with the diagram. So point at which the driver hits his brakes, the velocity at that position, we don't know what it is, that's what we're looking for, and the placement's going to be 0. Now 300 feet traveled, the time for that skidding of 300 feet, we don't know. The velocity at that time is going to be 0 because it's completely stopped, and the displacement's going to be 300. That's the end of the line where he stopped. Now, we know that the acceleration is -23 feet per second squared. Therefore, we're going to integrate acceleration to get velocity. And when we do so, we get velocity is going to be -23t plus c, and c is your constant of integration. We'll discuss that later in class. We then integrate velocity to get displacement, or in this situation, displacement will be the change in position. And in doing so, we get v of t is equal to -23t plus c. We will then do the get our displacement, and that would be -23t squared divided by t plus ct plus d. And using the fundamental theorem of calculus, we can solve this because we know we're going from 0 to t, and t would be the end of the line, literally. And when we do that, we're going to get the following. We're going to do the fundamental theorem of calculus, and doing so, we also need to get the initial velocity. Now, the guy says he was going at 55 miles per hour. We'll take his word for it at this point, and if we prove him wrong later, we'll prove him wrong. But we need this to get 80.67 feet per second. We did so using dimensional analysis. Now we can set up our equation. With that equation, we're going to get velocity v of t, and v of t would give you -23t plus 80.67. We know that velocity curve collects distance traveled. The distance function is given by this, the displacement. And when we integrate that, we get -23x squared over 2 plus 80.67x. Going from t to 0, we get this. S of t is equal to -11.5t squared plus 80.67t. Now, we know the time the car stopped, the v of t is equal to 0. We take our velocity equation. We're going to set it equal to 0. We get 3.507 seconds. We plug that in to the displacement, and we're going to get a value of 141.47 feet. We know that the driver, had he been traveling 55 miles per hour when he slammed on his brakes, the car would have traveled 141.47 feet. However, it skidded 300 feet. Therefore, the driver is definitively lying. He exceeded 55 miles per hour. Now, the distance traveled we can determine within this diagram. And you can see the area below the curve is going to be the distance traveled. This is a triangle, 1/2 base times height. We get a value here of 141.47. Now, we're going to work as a team. We're going to work in pairs to calculate the driver's speed at the time he applied the brakes from our previous notes. And we'll diagram as a group. And the diagram is something that's going to be critical to us. We'll project it on the board. But at this point, we'll work in groups. I'll pass out paper to make sure we can figure out the driver's speed.